Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on linear algebra, chapter elementary transformations, lecture number 10, in which I will prove some more theorems on equivalence matrices. Now we prove a theorem. Theorem is if A and B are equivalent matrices, then there exist non-singular matrices P and Q such that B equal to PAQ. Now we prove this. Given that A and B are equivalent matrices, that is B is equivalent to A. Therefore, from the definition of equivalent matrices, B can be obtained from A by a finite number of elementary transformations. We know that for elementary row transformation, of a matrix is same as pre-multiplication by corresponding elementary matrix with matrix A, and for elementary column transformation of the matrix is same as post multiplication by corresponding elementary matrix with the given matrix. Therefore, B equal to, we pre-multiply corresponding elementary matrices E1, E2, dot 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 ES, and post multiplication of elementary matrices F1, F2, dot 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 Ft, where E1, E2, dot 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 ES are corresponding elementary matrices for elementary row transformation. And F1, F2, Ft are corresponding elementary matrices for elementary column transformation. Let this is number 1, this is number 2. Let ES multiply E2 multiply E1 equal to P, and F1 multiply F2 multiply Ft equal to Q. Let this is number 3, this is number 4. Since we know that elementary matrices are non-singular and their product be also non-singular. Therefore, from 3 and 4, we get that P and Q are non-singular. Using 3 and 4 into, we get B equal to P A Q. Here this part is P and this part is Q, where P and Q are non-singular matrices. Therefore, if A and B are two equivalent matrices, then B is equal to PAQ, where P and Q are non-singular matrices. Proved. Now we prove the next theorem. Next theorem is, if two matrices A and B have same size and same rank, then they are equivalent. Now we prove this. Let A and B are two matrices of size m by n. Also, let rank of A equal to R and rank of B equal to R, same rank. This is number 1, this is number 2, this is number 3. Therefore, by elementary transformations, matrices A and B may be changed into normal form IR 0 0 0. This is the normal form of A and B. Since rank is R, so here we will get unit matrix IR, and this will be of size M by N. IR be the unit matrix of order R. Since this matrix is obtained from matrix A and matrix B by elementary transformations, that may be row transformations and column transformations. Therefore, IR 0 0 0 is equivalent to A, this is number 4, and IR 0 0 0 is equivalent to B, this is number 5. This is from the definition of equivalent matrices. Means if a matrix is obtained from another matrix by a finite number of elementary transformations, then this matrix is equivalent to A. Similarly, this matrix is equivalent to B. Implies that B is equivalent to IR 0 0 0. This is number 6, because the relation equivalency is symmetric. From 6 and 4 we get B is equivalent to this matrix normal form, and normal form of the matrix is equivalent to A. Then by transitive property B is equivalent to A. Therefore, A and B are equivalent matrices. Proved. Now, we prove the next theorem. Next theorem is let A be M by N matrix of rank R, and let NR be a matrix. Here IR, here 0 matrix, here 0 matrix, here 0 matrix. IR be the unit matrix of order R. Be its normal form or canonical form. Then there exists a non-singular M by M matrix P and a non-singular N by N matrix Q such that PAQ equal to NR. Now we prove this. Given that A, B and M by N matrix and rank of A equal to R. This is number 1. In R be the normal form of A, where in R equal to IR 0 0 0. This is M by N size matrix. Since in R be the normal form of A, therefore in R is obtained from A by a finite number of elementary transformations. Row and column transformations. We know that elementary row transformation of a matrix is same as pre-multiplication by corresponding elementary matrix with matrix A and elementary column transformation of a matrix is same as post multiplication by corresponding elementary matrix with the matrix A. Therefore, in R equal to, we pre-multiply A by elementary matrices E1, E2, dot 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 ES and post multiplication by F1, F2, dot 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 Ft, where E1, E2, dot 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 ES, F1, F2, Ft are corresponding elementary matrices. Let ES multiply E2 E1 equal to P and F1 multiply F2 multiply Ft equal to Q. Let this is number 3, this is number 4, this is number 5. Since elementary matrices are non-singular and their product be also non-singular, therefore from 4 and 5 we get that P and Q are non-singular. Using 4 and 5 in theory, we get here in our left side equal to, this is P, A, and right side be Q. This is number 6. Since in R equal to IR 0, 0, 0, this is M by N size matrix, is a matrix of size M by N. Therefore, left hand side of 6 is a matrix of size M by N. Therefore, the right side of 6 will be a matrix of size M by N. Since A be a matrix of size M by N, therefore number of rows of A be M. So for PA, the number of columns of P equal to M. Again, A has a number of columns. Therefore, PA has a number of columns. So, for PAQ, the number of rows of Q equal to N, means number of columns of PA equal to number of rows of Q. Therefore, P has number of columns equal to M. Q has number of rows equal to N, but PAQ has number of rows equal to M number of columns equal to N. Therefore, P is a matrix of size M by N, and Q is a matrix of size N by N. Therefore, from 6 N are equal to PAQ, where P is a matrix of size M by M, Q is a matrix of size N by N. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button. And if you have not yet subscribed my YouTube channel, then please subscribe my YouTube channel. Thank you.